Hey everyone, today we are going to do a extension of the Monte Carlo implementation from last time, and that's going to be Online Monte Carlo. So let's talk again about exactly what we're doing here. Monte Carlo, if you remember, is a method of model-free learning, and the reason it's model-free is because we don't have the MDP available to us. And so if we don't have an MDP that describes every little nuance of the environment, of how the different states work, all the different actions we could take, the stochasticity of where we'll end up if we took a specific action, if none of these pieces of information is available to us, then really the only method for us to estimate the values of the environment will be to interact with it. And so Monte Carlo's general method was, why not just play the game a bunch of times? Every time we play the game, go ahead and estimate the returns using the returns that we actually got, or the rewards that we got from playing that game, and just go ahead and play the game a bunch. And in the end, just directly average up all of the returns we got for the different states from all of our experiences. So that was the main idea. If you, again, don't remember any of that, go ahead and take a look at the last video because we will be just reusing a lot of that code. I'll put that video link down below and in a card above. This is going to be just a iteration on that video because there's one minor limitation of this Monte Carlo method. Although it's completely correct, it's that it's not an online algorithm. So an online algorithm is essentially something we can do in real time. But if I need to first play, let's say in this case, we have 8 games here. So if I first need to play 8 games and then I take the average afterwards, then there's some buffering period, right? So I need to essentially store all of my returns and all of my return history and trajectories and everything in memory. And then once I'm done, I can go ahead and take that average. But again, this is not the ideal way of doing it. Rather, we'd like to take an average as we're going. Right, so we're going to need to do something called an online averaging. Online averaging is nothing fancy, so let's just go ahead and look a little bit at the math. Very simple algebraic manipulation, and the form for online averaging is going to be extremely important going into future videos like SARSA, Q-learning, stuff like that. So let's go ahead and just take a look. So our main idea is, let's say we play K games. So we're going to say we're going to play K games. So we're going to play K different games, and from each game, we're going to store our trajectories and compute our returns. And we know that we call G our return. So for some, we're going to say QK, which is going to be the averaged Q values, right? So our average returns for a particular state action pair. QK is going to be equal to just the straight up average, right? Nothing fancy. We're just going to go ahead and average up our returns for those K games. I equals 1 through K. And again, going back here, that would mean that we play the game 8 times and then we average up our estimate for V1 for all 8 games. Our estimate for V2 for all 8 games, V3 for all 8 games. We just directly average them up, nothing fancy. And so that's all this is. So instead of the values, we're doing the Q value. So I'm writing Q here, but we're just gonna go ahead and average up our entire returns. And this is just standard averaging, nothing fancy. But this requires us to first play K games and then take the average. And what I'd like to do is take the average as we're going, right? As we're going. So it goes a little bit faster, less memory usage. And this is known as an online algorithm because we're computing something we want just as we're going. And so to do this, let's just go ahead and write one thing else. Our Q of, or back Q, K plus 1. So let's say we played K plus 1 games. Instead of just K games, we played K plus 1 games. Well, the formula is going to be the same, right? 1 over K plus 1. And then it's going to be the sum from I equals 1 to K plus 1 GI, right? We're just going to go ahead and average up K plus 1 games. If I write it like this, I can also equivalently write this as this, no problem. I can keep the 1 over K plus 1 here standard. And actually, let's go ahead and just write it over here just to save some space. 1 over K plus 1 stays. But then we have the sum of GI from I from 1 to K plus 1. So that's going to be essentially G1 plus G2 plus ... G K plus 1, right? That's what I have. Let's just separate this sum out a little bit. Let's write this as the sum of I equals 1 to K of GI. So that's going to be everything from G1 to GK, but we also still have this GK plus 1, right? The K plus 1th term. So we're just going to go ahead and add that right here. right? So all we've done, taken the sum and just separated. It's still a sum, but I just rewrote it this way for convenience. Now, one other small manipulation we're going to do is we can see we have this term right here, sum of gi from 1 to k, and we also see that term right here, sum of gi from 1 to k. And so we can rewrite this as the sum of gi from I equals 1 to k as just cross multiply. We can take this k and just move it up here. So it's going to be k times qk. Right? Nothing fancy, just a cross multiplication. So that means this term here is really k times qk. So let's go ahead and write that. That's going to be 1 over k plus 1. And then inside we're going to have k qk plus g k plus 1. And the reason we're doing this is because I want to find a relationship between my q values at the kth time step and the k plus 1th time step, or basically, number of games. I want to find this relationship between the two so I can write an iterative formula to solve it one step at a time, to take the average one step at a time rather than having to take all of it at once. So algebraically, nothing's really changed here just yet. We've just done a couple of substitutions and rewrote some stuff. So now that we have this, let's go ahead and do a little bit more manipulation. We're going to distribute this k plus 1 to both of these terms. So let's do this will be k qk over k plus 1. And then we will have, again, we have the g of the k plus 1th term over k plus 1, right? And again, remember, gk plus 1 is my returns that I got from playing the game k plus 1th time. So this is the k plus 1th game that I've played. qk is my estimated returns, basically the average, as you saw before, up to k games, right? So that's the interrelationship between the two and what's the difference between them. So we have all of this, and now let's just go ahead and use our handy trick that we use all the time. We're going to go ahead and just add 1 and subtract 1. So what does that mean? Let's go ahead and write here k over k plus 1. We're going to rewrite this as k plus 1 minus 1 over k plus 1. And that lets us write this as k plus 1 over k plus 1. This is going to be 1 minus 1 over k plus 1. So that's just a little handy trick, just so we can separate out some terms. And we can go ahead and substitute that back in. So we have here, let's see, this term right here, 1 over k plus 1, is just going to be all of this stuff over here. So we're going to write 1 minus 1 over k plus 1. That's our first term, times the qk, right? The qk term that we had right here, plus this will stay the same, gk plus 1 over k plus 1, no problem. gk plus 1 over k plus 1. And again, this is what our qk plus 1 is equal to. So we got that. We can go ahead and distribute some of this stuff around. So this qk, we can multiply it in. So this is going to be equal to qk minus qk over k plus 1. And then we have, again, this term from before, nothing changed, gk plus 1 over k plus 1. That's our standard setup. And now we can go ahead and do the last step, and let's just write it all out, qk plus 1. So that's this qk plus 1 is equal to, it's going to be, we can take the k plus 1 as a, out, we can take it out. So we can do qk, that's this term right here. And then we have this k plus 1, 1 over k plus 1 term. So let's go ahead and pull that out. It's going to be plus 1 over k plus 1. And then we have a gk plus 1 minus qk. gk plus 1 minus qk. And this is our new update rule. So our qk plus 1, so my average, my running average up to the k plus 1th game, can be written as the running average up to the kth game plus this formula here. So my new return that I got on the k plus 1th game minus my current estimate up to qk, and then times 1 over k plus 1. So this is a very standard, if you've ever seen online averaging before, you have seen this formula before, just in a slightly different form, but nonetheless, this is online averaging. And notice that we just essentially got a recursive relationship, right? Or an interdependent relationship between the time steps or game steps. So instead of having to do this, of let's just go ahead and play k different games and then average after the fact, I can now just iteratively estimate my average as I'm going, right? As I'm going. So I can find I'll first find my Q1, and then I'll use Q1 to find Q2, Q2 to find Q3, Q3 to find Q4, ... And Q1, or Q0, I guess, our starting step, we'll just start as zeros because at the beginning, the average is 0. And then iteratively, we will continue adding and averaging up to that time step. So again, this is not so important in terms of results. It gives you exactly the same results as before. This is just a better algorithm, and this form will become even more important when we look at it in the future. So let's go ahead and implement it, right? Nothing too crazy. So like I mentioned from before, we're going to be reusing all of the code that we wrote last time. So the ability to sample a trajectory from a game, we're going to reuse that. To compute our returns, right? To compute our returns, we're going to be reusing that. And then this was our Monte Carlo estimation from before. And this is what we want to avoid. So from our code from before, notice that we first play however many games we want. And then after we've played however many games, then we loop through and average everything together, right? That's what we're trying to avoid. We have a for loop, and then we loop through all of the states and average them up. Rather, what we want to do is every time we play a game, we then want to update it instead of kind of waiting to the end to play all the games. Because in this case, we have to store information for every single game, in this case, 5,000 games, inside memory. But in the other case, we can just store up to what we need and then just update all of our accumulations or accumulated averages and then delete it. And then we can go ahead and run another game, grab our new trajectories, and then update those values and then delete them, and then so on and so forth. So there's no need to just store everything all at once. So let's go ahead and implement it. This was our Monte Carlo policy iteration. So I'm going to go ahead and just run all of this. Policy improvement, right? Standard policy improvement. The Q value we want is the action we want is essentially the action that with the highest Q value at every state. So there you go. Just take the argmax. And then this is going to be our Monte Carlo policy iteration. Essentially, we'll let that run. It takes just a second. And then this is our attempt to test a policy. So we can see in this case it didn't do all that well. Different runs will give different results because this is a stochastic process. It takes, a little bit of luck is involved when getting these results. All right, so either way, we can ignore that. Let's just keep going. Let's implement our online Monte Carlo. So to do this, we're gonna do def online Monte Carlo estimation. First, we're going to give it our policy. We need the environment we're playing with. Again, same environment as before, the frozen lake. We're going to give a gamma, our discount factor, 0.99. Max steps. This is the longest a trajectory can be. Let's just set it to 50. Let's be it done. And then num episodes. So how many games do we want to play? Num episodes. And this is going to be 5,000 is what I set it to. So that's what we'll do. And this is our update formula from before that we just derived. So let's go ahead and just implement it. So how this is going to start is Q is going to be np.zeros. Q values will start out as just zeros because we don't know anything about them yet. And this is going to be in the shape of env.observation space. So the number of states by the env.action space.n. So by our, and it's also going to be .n. So it's going to be our number of states by our number of actions. Standard Q table. And what we're going to do is we need to actually keep track of the number of visits to every single state action pair. And that's our K, actually. So if you remember, K is our averaging. So when we just average stuff together, it's going to add up how many times did we visit that specific state divided by, the number of times visit. So it's standard average. And so what we need to keep track of is just how many times did we visit every single state action pair. And that will essentially be our K, because when we average, that's what the K would have been. How many times did we visit that specific state action pair? And then we just average all that information together. So we're going to do n is equal to np.zeros. And it's going to be, again, same thing, env.observation space dot n, env.action space dot n. And this is just going to be a buffer that's going to hold on to how many times you visited those different state action pairs. And we're going to do for blank in range num episodes, right? So how many games do you want to play? In this case, we're going to play 5,000 episodes that we're going to average. And then we're going to go ahead and sample a trajectory. It's going to be the sample trajectory. And again, to sample a trajectory, we need to give it our current policy, which is just kind of whatever it is right now. It starts random. We need our environment, and we need max steps, right? So what's the maximum length of these trajectories that we want? And so then our returns is going to be compute returns for that trajectory with our discount factor gamma. And so all of this up till now is exactly the same. We went here, we sampled a trajectory, we got our returns for an episode, and then in the next step, what we did is we stored these returns in a dictionary. So then we could average them together later on. But we're going to avoid that step now and just directly use our Q value update using an online averaging like we have up here. So let's go ahead and do that. What we're going to do is for state action G in returns, and actually let's just go ahead and print out returns here just so it's clear. And let's go ahead and play a game. Let's do policy. There we go. Just sample a random policy here. So we're just saying for every single, in our action space, basically for every single state, pick some random number between 0 and however many possible actions we have available to us. So there we go. That's our policy. If we look at it, there you go. That's our randomly sampled policy that will hopefully improve over time. And now we can go ahead and do online Monte Carlo estimation. We'll give it our policy, and then we'll give it our environment, and everything else can be the same. And you can see here, our returns are returned as a dictionary of for this specific state action pair. So whatever state 4 action 2 is, this is my return. For this state, this action, this is my return. For this state, this action, this is my return, dot, dot, dot. That's my state action pair. So that's my return. And so we're just going to loop through them. We're going to do for state action and G, right? So G is our return in returns.items. First of all, let's go ahead and update our Q values. We know our Q values follows this formula here, the online averaging. So our new Q value for this specific state action pair is going to be equal to the existing Q value. So QK plus 1 is going to be the existing Q value for this state action pair, plus let's just go ahead and do the K plus 1 denominator in a second. We'll do the top first. So first, GK plus 1, that is our current return. That's this G right here, G, minus our QK, again, our current estimate, state action, just like that. And this whole thing is going to be divided by K plus 1, right? K plus 1. So that's just going to be divided by N, right? So N is our dictionary, or basically matrix of how many times did we visit this specific state action pair. In this case, is there's nothing in it yet, but that's fine. It's going to be state action plus 1. So that's our K plus 1 in the denominator. We have our G minus QK, so G minus QK. And remember, Q currently, before we update it, is our estimate up to the kth time step. So this Q is QK. We're updating it to become QK plus 1 for the next time step, right? For the next iteration. And so that's our update of our Q function, Q values, right? Online averaging of our Q values. And then we're going to go ahead and do our state action plus equals 1, because we have visited the state action pair once, because we see right here, we've visited the state action pair. So we need to update our N to make sure we're averaging correctly as we're going. And that basically covers everything. That's our update rule. And we can then, after we're done with all of this, we return Q. And this, again, is so different from what we were doing from before, because notice we don't have to store all of these intermediate stuff just to average them up. All of this extra storage we had to do here to just go ahead and average them after the fact no longer exists. So the memory cost is obviously lower because we don't need to store all of my return information for 5,000 different episodes only to average them at the end. All I did is just use my iterative averaging method, so we get it all in one go without having to store those intermediate states. And there we go. That's my estimated Q value for this specific game. Good. Now that we have all of that, we can go ahead and do our Monte Carlo policy iteration method. This is going to be identical to what we had before. We had this Monte Carlo policy iteration right here. So I'm going to go ahead and just copy all of this and stick you right here. But instead of using standard Monte Carlo estimation that we had before, we're going to use the online Monte Carlo estimation. So there we go, online method instead. So nothing changed, just using my new online Monte Carlo, and there we are good to go. So we can finally go ahead and train our model, right? So again, all existing code from before. We're going to go ahead and get our optimal policy, which looks like it's this, and our optimal Q value, and that's basically it. And we can finally test our policy and see how it goes. And we can see in this case, not doing so well. We can play a bunch of games, and sometimes it'll work well, sometimes it won't work well, and that should be fine. Right, so in this case, we can see it got almost 80% accuracy. So due to the stochasticity, maybe having a larger number of episodes or something like that would help, or maybe messing with the gamma as a hyperparameter, or increasing or decreasing the number of steps we can take. All of these things have an effect on our overall results, but we can see every once in a while it does seem to work reasonably well. So we're good to go. Now, there is one kind of little caveat, and something, again, which is going to make this closer to TD learning that we haven't talked about yet, but we'll talk about next time. And that's this 1 over k plus 1. 1 over k plus 1 is technically just it's just a constant, right? It's just a constant that we keep track of with this n matrix, right? How many times have we visited that state, so we can properly do our running average, which is all well and good. Now, the thing is that instead of doing 1 over k plus 1, what if we swap it out for something like a learning rate, right? Instead of using 1 over k plus 1, which just essentially as k increases, 1 over k plus 1 will decrease. And instead of doing that, why not use some kind of a learning rate like alpha t? And alpha t will be some time-dependent learning rate parameter that's completely up to us, right? We can decide what that learning rate should look like. And you can kind of mess with it. It's just a hyperparameter. So let's just go ahead and create a simple exponential decay. Def learning rate scheduler start. We'll have some start value. We'll have some min value. We'll have some decay factor, right? The exponential decay factor, and num episodes. Right, so the question is, what is the, so the starting value, let's say our alphas, is going to be the learning rate scheduler. And the start value will be, let's say, 1. We'll the minimum value, the lowest value we'll do is 0.01. And we'll decay with a factor of 0.99. And let's say we have 5,000 steps. Okay, so we can implement this. Alphas is then equal to start val times our decay factor, right? So times decay factor to the power the number of episodes. For episode in range num episodes, right? So there we go. So if we print out our alphas, you'll see you'll get values like this, right? All well and good. So this is my learning rate parameter for all 5,000 steps. But notice what our values kind of become. These values are essentially 0. E to the negative 22 is basically just 0. So that means our Q values would not really be able to be updated at these larger time steps, because we're just going to be multiplying our difference that you see here. We'll be multiplying gk plus 1 minus qk. We'll be multiplying it by a value that's basically 0, which means our q's will essentially be stuck. And this is why I'm setting some min value. So if my alpha is less than the min value, then just clip it to the min value. So some learning can still happen, or some updating can still occur. So we're going to do alphas is equal to a if a greater than or equal to min val, else min val for a in alphas, right? So just loop through all of my alphas, and if it's less than our min val, then just make sure it's min val. Otherwise, just leave it alone. And so we can now return alphas. So now we have a nice little scheduler, and you can see all of my later time steps are just 0.01, but we have essentially this decaying learning rate, which is exactly how 1 over k plus 1 works, because as k increases, 1 over k plus 1 will decrease. And just to make it very clear, plt.plot alphas, and there you go. We have this kind of decaying thing, and you have this clip at the end. So you can see we've clipped it at 0.01. Now that we have all that, nothing else is all that fancy. We just need to go ahead and just update this method right here. So we had our online Monte Carlo estimation. Let's just copy it and paste it down below. But instead of using just estimation, we're going to do with learning rate, right? With the learning rate. And in here, we're going to pass in a couple of extra stuff. So we have everything that's in there already. We're also going to have our learning rate start val, and which let's just set it to 0.8, so it's not just 1. Then learning rate min val 0.01. I just picked random numbers, and then learning rate decay factor 0.99, just like that. Most of this code will stay the same. We still need these Q values, but we're now going to have alphas, right? So we're just going to go ahead and grab U. Instead of n keeping track of that 1 over k plus 1, we're going to have some alphas, our learning rate. And it's going to start at learning rate start val. It's going to end, or the minimum will be the learning rate min val. Here is our decay factor, and then here is the number of games that we want to play. So there are our alphas. All that changes now is instead of doing divided by n, basically divided by k plus 1, as you see here, we're just going to multiply it by alphas I. So we can go ahead and do alphas I times that. So again, nothing changed. We just have alpha, our alpha learning rate term, hyperparameter, how we want to set it up, times this, rather than 1 over k plus 1 times this. Doesn't really change much. It's just a nice thing to have. And of course, we don't need u anymore either. So all we're keeping track of is this. So this isn't exactly a running average, but it is like an exponential average, right? Where you're weighting initial things higher, weighting later things lower, things like that. So we now have our, again, online Monte Carlo estimation. Everything else is identical. So we can go ahead and update our policy iteration method one more time. And this time, we're going to have our, we're using the online Monte Carlo estimation, but with a learning rate, right? So we're using the learning rate instead. Everything else is identical. Looks like there is a bug. There is no I, and that's because I need this, right? So the alpha is dependent on which episode are we currently on, right? The alpha is across the number of episodes, so I actually need the I here. So for I in range num episodes, we can now grab the ith alpha term. There we go. All right, and then finally we can test our policy. Again, it's always a little random. Looks like this time it did not work out so well. This time a little bit better. Every time you run it, this time looked like it didn't converge at all. Very poor. And this could be a factor that we need to mess with our learning rate values a little bit, see what works well, see what doesn't work well, and essentially optimize or do some hyperparameter tuning of these specific values. In one of my runs, of course, this is somewhat luck. We got 74% accuracy right here, or not accuracy, but 74% success rate. Without an MDP. So when you don't have the MDP, there is a little bit of randomness in the game, right? There's randomness in the learning, and there's lots of things we can try to do to stabilize this. We're going to see some really important ones later, like TD lambda and stuff like that. But for today, this should be fine, just to give a general idea. So this time, looks like we got a solid run here, right? That's a good policy success rate. All right, perfect. So I'm going to call it here. In the next video, we will expand this entire notion, because this formulation right here is extremely important and will feed into SARSA and Q-learning, and essentially the class of TD learning methods, right? TD learning methods. This will be especially important, so we will look at that one next time. I will see you all in the next one.